Are we good? Thank you for coming, everyone. Today, we're going to talk about KubeRay, which is a Kubernetes Ray clustering solution. Let's first start by introducing ourselves. My name is Ali Kanso. I'm a principal engineer at Microsoft, and we use Ray as part of a product called Bonsai, which is a machine teaching as a service. And at the heart of it, we use reinforcement learning, and we use Ray RLib for that purpose. And my colleague here is Jia Shin.
This is Jia Shin. I'm from ByteDance infrastructure team. ByteDance has a portfolio of applications in over 150 markets and 35 languages with almost 2 billion monthly active users. And AI and machine learning are the heart of the ByteDance technology. So Ray is being used in those research scenarios with special focus on some domains like graph and batch prediction for ads and search. Yeah, that's it. Hand over to Ali. Yeah.
Thank you. So just as acknowledgements, KubeRay is an open source project. We want to thank the Anyscale team, Dimitri, Philip, the others that really helped us with it. All the contributors, we have roughly 40 of them now, and all of those supporting this work in general. So shout out to all of you, and thank you for your support. So today we're going to talk about machine learning frameworks and how machine learning is distributed in a generic way, which requires a generic framework and a generic solution for that framework. That brings us to Kubernetes operators. And then we introduce KubeRay, and after that, we go into the new features of KubeRay, and we finish with the future plans. So starting with machine learning, today we've heard it many times over. Machine learning is omnipresent. There's a recent study done like 2 years ago. From 2018 to 2020, there has been 14,000 journal papers on machine learning and its application. And this is not just academic work. So if we look in practice, the edge devices where machine learning models are being deployed, where inference is happening, those are wide-scale deployed right now. So to give an example, Raspberry Pi 4 has now quad cores and 8 gigabytes of RAM. That used to be considered like a full-fledged laptop device or workstation. And now it's simply just an edge device. If we look at a car is considered an edge device, and the car has 100 million lines of code on it. A Tesla self-driving car has 150 million lines of code. So to put things in perspective, Linux kernel has like 28 million lines of code in GitHub. So your car now has like equivalent of 4 Linux operating systems running on it. So to do inference and to deploy machine learning on the edge is very feasible today. It's very doable. Now, the thing is, machine learning is still very compute intensive. If we think of hyperparameter tuning, matrix multiplication, and so on, by nature, training is compute intensive. And how do we usually handle or mitigate this, this compute intensive workload? We go to distributed deployment models. So basically, when we think about distributed machine learning, there's no single solution for it. It can be a centralized approach, like with ensembling. We can train on a subset of data, and when it's time for prediction, we can just do aggregation, or we can do, for example, with parameter servers, we can do decentralized type of distribution. So basically, we need a generic distributed machine learning framework for that. And this is where the Ray solution comes into the picture. So Ray basically has 2 things going on for it. First, it's a universal framework for distributed computing, which means it can handle a variety of workloads. And the second thing is it's an ecosystem. So there are many libraries that you can integrate and run on Ray, and that gives you the versatility of running distributed workloads for different machine learnings there. Now, the thing is, if Ray is handling distributed computing, how is Ray itself deployed? And this brings us to the architecture of Ray. So at a very high level, we have Ray distinguishes between a head node and the worker node. So the head node is the one that will have the global control store, and the worker nodes will, at runtime, when they're instantiated, they will register with that head node, and the head node will be aware of their presence. Now, each node can have a worker. And here we distinguish between a worker node and a worker. So when we say node, what we mean by node is just a computing environment. So it could be a virtual machine. It could be a physical machine. It could be a Linux container. That's what we mean by a node. Now, a worker is just a way of executing workloads, and this is just the Ray terminology there. Now, if we go a bit deeper into this, so this is just a simple example. We're showing here 4 tasks that we're defining in our code. Now, those tasks are going to be deployed on Ray workers. Ray workers are executing on Ray nodes. And the question is here, who's managing the Ray cluster itself? Who's scheduling the worker nodes? Who's scheduling the head node? Who's taking care of cleaning up the cluster when we're done? Who's taking off upgrading the cluster, and so on? And this brings us to where we want to deploy our cluster. And today, we're going to talk about Kubernetes. Because ideally, what we want is to have a computing platform that's capable of handling not only the scalability of machine learning workloads, but also the scalability of Ray itself. And here we chose Kubernetes mainly because it's already battle-tested architecture. So Kubernetes is the de facto container management platform. At Microsoft, we run Microsoft Office 365 on Kubernetes. We have over 200 million monthly users for that. We run GitHub APIs, Microsoft Teams, over 100 Azure services run on Kubernetes, and AKS more specifically. Now, the way Kubernetes works is, as a user, you really don't have to understand this architecture that I'm showing here. You just have to provide the control plane with the desired state. And then you'd have controllers that are relentlessly trying to make sure the desired state and the actual state are the same. Now, the unit of scheduling in Kubernetes is a pod, and the pod is just one or more containers. A container is just an instance of a container image at runtime. Now, if Kubernetes is capable of scheduling pods and containers, does it know how to schedule Ray clusters? And the answer is no. Kubernetes has no notion of what's a head node, what's a worker node, how they should be instantiated, and how they should start up. So this brings us to KubeRay. So KubeRay is specifically there to extend Kubernetes with the knowledge of something that we call a Ray cluster. So Kubernetes does not know what a Ray cluster is. We extend it with the Ray operator and with some custom resource definitions. And the Ray operator is simply an extension, think of it, of Kubernetes that understands what a Ray cluster is. And at runtime, it can create, update, delete, and so on with Ray clusters. So if we dig a bit deeper into the operator mainly interfaces with the Kubernetes API server. So basically, it has that interface. We can logically, and I emphasize on logically here, split that interface into 3 different parts. There's the part that watches for user events. So if the user creates a Ray cluster definition, or updates it, or deletes it, the Ray operator is watching for those events and reacting on them. The second interface is the operator trying to create the Ray cluster artifacts. Those are the pods, the services at runtime, and making sure that the desired state and the actual state are the same. Finally, things can happen at runtime. A pod, for example, can fail. And the operator is listening to those events. So it's listening to cluster failures and reacting to them. So when we put all those together, we get a KubeRay, which is the solution for managing Ray clusters at runtime. Now, the question is, why not just use a Kubernetes deployment? I mean, a Ray cluster is just a group of pods. A Kubernetes deployment or a stateful set, that's also a group of pods. So why not just use what's already supported by Kubernetes natively? Now, there are many reasons why we don't do that. I just listed a few of them here. First of all, we can have multiple worker groups within the same Ray cluster. And work group is a notation that we're defining in the KubeRay. And basically, within one cluster, you can have different groups of workers. Some group of workers may be using GPUs. Others may not. So they can have different resource requirements, and you can define that as a configuration at runtime. The second thing is, with worker groups, you can scale them up and down. And in Kubernetes deployment, for example, scaling up and down with the horizontal pod autoscaler, it's done randomly, especially scaling down. So Kubernetes will just randomly choose a pod, and it will go ahead and remove that pod at runtime. In our case, this is not acceptable because we don't want to just remove a random pod. We want to remove a pod where we have no actors and no tasks executing. So it's not based on just resource utilization, CPU, and memory. We have other criteria here at play, and Kubernetes deployment does not allow us to do that. And finally, we have that order of instantiation. So the head pod needs to start first, it needs to be ready, and then the worker pods can go ahead and register afterwards and connect to the head pod. So for all those reasons, a simple Kubernetes deployment cannot do the job, and we need a smarter workload manager that's capable of doing that. So if we look at the cluster creation in Kubernetes by the Ray operator, it starts by reading a cluster configuration. It generates the head pod parameters, creates the head pod, creates the head service, generates worker pod parameters, wait until the head pod is ready, and then the worker containers will be created. And this is the logic followed every time you create a KubeRay, with KubeRay, a Ray cluster at runtime. Now, we talked about KubeRay under the hood, how it's working. The thing is, from a user perspective, you really don't need to know about any of the things I just talked about. From a user perspective, you're defining a Ray cluster either as a YAML JSON file, and you can use kubectl to deploy it. You can use the CLI or any Kubernetes client, Python, Golang, C#, etc. Or you can just create a template for a more configurable way of deployment and just use Helm in order to deploy your Ray cluster. From a user perspective, you really don't know that the KubeRay operator exists. You don't need to know. It's just there in a Kubernetes cluster, and it can handle your requests. Now, if we look at the configuration, how it looks like for a Ray cluster, we basically have two different pod templates. One of them would be for the head pod. We're defining what type of image we want to use, what type of configuration we want to pass for it. And then we have the Ray workers. And in the Ray workers, there's a big distinction here, which is the minimum and maximum number of replicas. So you can define as many replicas as you wish for your Ray workers. And the second thing is the worker group specs, it's an array. So it's not just a single instance, meaning that you can have different worker groups. Each worker group can have its own resources, different CPU limits, memory limits, and so on. So basically, it allows you to configure your cluster to your liking, and then you can update that cluster at runtime. Let me go to a very quick demo here. So what you're seeing is simply a kubectl create command, and we're just passing a YAML file for it. And on my right-hand side, you will see that now we have a cluster created. The head is running. The workers are waiting. They are in an init state. And after that, they will be initializing and running. You can also see that we have a head service that's abstracting the head pod. And all of that, all of this process, it kind of happens within less than 10 seconds. So in the next slide, I'm going to show some experimental results. And in this particular case, we had two different groups. We have a medium group and a small group. The small group has 3 instances. The medium group has 1 instance. And this is how easy it is for a user to set up a Ray cluster. It's just a kubectl create command passing some YAML file. So in terms of performance, there are different things happening, some of them happening in parallel. But the time for Kubernetes to react to the creation is roughly 600 milliseconds. Time to create the head service, and for the head service to be in the DNS, to appear in the DNS, that's roughly 1 to 2 seconds. We have the head creation time, which is 3 to 4 seconds. And then when the head is created, the workers will come up and be ready. And that's, again, like 5 to 6 seconds. So in total, you can just assume that a cluster creation will take roughly 10 seconds. You should account for it. And from there on, you would have a KubeRay cluster. You would have a Ray cluster managed by KubeRay up and running. And you can update it. You can add nodes. You can remove nodes from it. You can delete it. All of that happening at runtime. All of that could be happening with Kubernetes kubectl. You can use other tools if needed. And all of this would be happening for the user without the user being aware that there is an operator and there is KubeRay running in the background. So next, we're going to talk about the new features in version 0.3 of KubeRay. We're going to talk about the community plans. And this is the part where Jashin and I have been working for roughly a year on an open source project. And this is the beauty of a community gathering like this. Like, we're not in the same company, but we meet every week, we collaborate every week, and we have a common interest in seeing this becoming a very successful project. So, Jashin?
Great. Yeah, but by the way, we just officially released 0.3 last week. We got 24 contributors and contribute over 140 PRs and to accomplish the goal. And that's a great community effort, as Ali mentioned. So the first part, we would like to talk about the autoscaling. Autoscaling actually has been added to 0.2, but at that time, it's not that stable, and the recore part doesn't have the solid integration. We use specific version to support autoscaling. But now in 0.3, it's stable, and we expose more like configurations on the autoscaling side. Ray can actually automatically manage underlying resources based on your application metrics through the autoscaler. So this is a critical, important component. So in the integration here, we enable the option for users to specify whether you like to enable autoscaler or not. If so, you will see in your cluster there will be a new component added, which is the autoscaler. So I'll explain how it works, how we make it work. From a recluster management perspective, the integration has some challenges. The challenge is more on the splitting the responsibilities of the lifecycle management and the autoscaling. So we actually make this through some like mechanism to clearly define the boundary of the autoscaler component and the recluster component. So the lifecycle management will only take responsible for managing those nodes, for example, like adding nodes or deleting idle nodes. But the autoscaler side, you need to read the metrics from the monitoring system, which is provided by Ray itself, and then make the decision whether I like to add some nodes to the cluster or delete some idle nodes, some target idle nodes. So the boundary is very clear, which makes the architecture very clean and straightforward. I'll use the following example to explain more details. From the code perspective, that's what we did to implement this KubeRay autoscaler provider. So in the recore part, there's an interface called node provider, and this is the wrapper of those like cloud APIs. If you see the implementations, we'll notice like there's AWS solutions and the GCP solutions. So we add a Kubernetes Kubernetes operator provider to play the similar roles. But the different part is in AWS, actually the node provider interact with the cloud API directly. For example, I add an instance, then it calls the EC2 API to add a like target instance. But in Kubernetes, since we talk about the boundaries and the responsibilities here, right? It just used to update the Kubernetes resource, the custom resource. It just tell the customer resource, okay, what's the desired state? And the rest of the process will be automatically handled by the Ray operator itself. So I'll give a like example how it works. The diagram is from Dimitri. Dimitri gave a talk Ray meetup to explain how autoscaling works here. So I borrowed the diagram. So imagine the user, when user want to submit a workload, in this case, let's say it requires 4 GPUs, the workload requires 4 GPUs. And when it submit to the cluster, the rig head we have the mechanism to detect, okay, the cluster doesn't have enough resource, and then it forward a resource request with 4 GPUs to the Ray autoscaler. And what Ray autoscaler does is it will do some like calculation, run some algorithms to check, okay, how many nodes we needed and what type of the node we needed. And then it will patch the KubeRay, it will patch the Ray cluster custom resource. That's what we talked the KubeRay node provider plays a role. It patched the resource that, okay, I need an extra, like a replica of the target node group. And the KubeRay operator side will watch the resources, any changes on the cluster. Once it detects there's a change on the cluster side, it will take the action to scale up. In this case, we will add a node with 4 CPUs and add to the cluster. And once the node is ready, then the original workload we submit to the cluster can be scheduled. The second important feature we deliver in 0.3 is fault tolerance. So people actually can enable some high available backend storage, for example, HA Redis cluster, to use that for the GCS server. So that means once you use the HA backend and some annotations like I specified, highlight here, like FT enabled, then the KubeRay controller will add the readiness prop and liveness prop to the head node. So that means that underneath the Ray cluster will watch all the events from those props. The props will detect the local Ray dashboard agent and relate to check whether the head node is in healthy state or not. If not, it will delete, it will kill the head and recreate the instance. Your data won't be lost because if you enable the high available backend, then the GCS kind of becomes stateless. So all your cluster data is there. So that's a very big improvement to, on the Ray cluster stability. So that's the 2 major features we delivered. Then we talk about the workloads. So the first one is the Ray job. We introduced a new custom resource in this release. Imagine how you submit the workloads against a remote cluster in the past. We create the cluster, get the endpoint, and then we feed the Ray address into the Ray init method, and then run the program. It's like a client mode because the driver itself runs outside of the cluster. Ray job actually has been introduced in Ray core since 1.9. It solves the problem like you can, it provides a lightweight mechanism user can package and submit your workloads, manage your applications as jobs. So that's pretty helpful because you can submit the entire driver program inside the cluster. There's no client anymore. But the tricky thing is the users still need to provision the cluster and then submit the workloads in 2 steps. This can be definitely addressed by some orchestration tools, but with additional efforts. What we did here in KubeRay is we make it serverless. User can just provide a Ray job manifest. You can type the application configurations and the cluster resource requirements. Then KubeRay controller will automatically handle all the lifecycle stuff for you. If we check the pseudocode here, it creates a cluster and submit the jobs, and periodically check the job status and report to the custom resource. And after the job is done, the cluster resources will be released automatically. I think that's a perfect way to run Ray jobs on Kubernetes. Another critical features provided by 0.3 is Reserve. I think Ray Summit have the dedicated session for this part. The overall idea is very similar. So Reserve is a perfect way to run Reserve on Kubernetes because it shipped a lot of features, for example, like health checking, like status updating, upgrade, etc. I think everything is automated. People can interact with your own applications on the on the Kubernetes. And a lot of configurations can be updated in flight. For example, if you upgrade auto-scaling config for your inference servers, everything's automated. Another powerful tool is the deployment graph. You can build a very complex inference graph in single Ray service. So that helps you solve the like microservice topologies automatically. Okay, let's talk about the community efforts and future plans. So currently, there's two communities adopt KubeRay, and they have a very solid use case. The first one is the Kubeflow, which is the open source machine learning orchestration solution natively designed on Kubernetes. In the POC work, Kubeflow baked the KubeRay manifest in the distribution. So that means that is deployed with other core components like Kubeflow pipelines, training operators, Cartib, etc. So Kubeflow users can interact with Ray clusters in their isolated multi-tenant notebook development environment. That's a very good supplement to the Kubeflow ecosystem. Flight is a distributed engine, especially for those like machine learning workloads and data processing workloads. And Flight provides a solution to orchestrate your machine learning pipelines. So they implement a task plugin. So that means all the complexities to run Ray applications, which is solved by KubeRay, they encapsulate those pieces in their task plugin. So that means whenever you build a pipeline, people can use Spark for data processing, and then rest of the AI process hand over them to Ray using the task plugin. So that has been released already. Okay, in next release, I think we'll concentrate on improving some stability of the alpha features like the Ray job and the Ray serve, and also reduce the barrier for users to adopt the KubeRay, including like documentations, docs, examples, and deployment, those tutorials and docs. And there's another few interesting features we plan to do. That's early stage proposals, the plugin to scale up and down the node groups, and some node failover handler, and also some Jupyter Lab plugin to further reduce the gaps between the operations and development. Yeah, that's all the update from my side. Yeah, thank you guys.
Hello, thank you guys for your presentation and community work. So I have a question about images that you create for worker nodes. So each use case have particular requirements for TensorFlow libraries or so on. So do you maintain those images separately and specify it in the configuration file, or you do it through like a Ray job to install like CUDA libraries and so on? And the second question is garbage collection. So you rely on users to create clusters, but do they also have to like garbage collect their clusters after they're done? Thank you.
Thank you. Yeah. So for your first question, there are two ways of doing things. One way is to consider the default Ray image as just as a base image, and then from there, do a multi-stage Docker build and add your own image or your own application to that image, and then use that one here. So the KubeRay does not really understand that this is a pure KubeRay image or Ray image versus your own image that's built on top of the Ray image. For example, in our use case, we bake our application on top of the Ray image, and we just use that. Now, another alternative is what you exactly just mentioned, is just build a generic Ray cluster and submit Ray jobs to this cluster, and that's how your application can run on there. You had a second question about garbage collection, and today we rely on the user common sense to clean up their clusters after, but I don't know, there might be something in there, like specify termination or expiration period for the cluster, that might be a flag that we can provide if we see there's a lot of uncollected clusters that are just laying there doing nothing. Yeah.
Actually, I think that's probably the only question we can take. The next session is going to come in 15 minutes, but I think the speakers will be around for questions after the talk, so feel free to talk. So thank you, everyone, for attending. Give a round of applause for our speakers.